All right, here we go. All right, so welcome back. This is the virtual residency 2021 workshop at the introductory, intermediate, and advanced levels. It's Monday, June 7th, 2021. This is the mid-morning session, Effective Communication. I'm Henry Neeman, and I'll be presenting, so let's dive right in. And I want to reiterate, I really strongly encourage you to ask questions during the session, either in the Zoom chat or by voice. Either way is fine. I love questions, and I confess that I only have 62 slides for 75 minutes. So if you ask me questions, then I won't be doing my usual 1 slide per minute. I'll be able to use up the whole 75 minutes. So don't be shy. All right. So a quick outline, we'll talk about research terminology as a really important component of how to talk to researchers. And then we'll look at researcher types and the mindset gap, what to say to a researcher, how to find researchers, how to find their projects. And we'll even look a little bit about, if you're going to write a grant proposal, how do you, what questions do you need to ask related to that? Somebody asked, are the slides already posted? Yes. So I'll put here is the URL for, in the chat for the workshop. So if you just go to that URL and you scroll down to the effective communication session, you'll find the slides. They're already posted in PowerPoint and PDF form. By the way, if you want to steal my slides, I don't know about others. I don't speak on behalf of other speakers and panelists and moderators. But for my slides, if you want to use them, you are welcome to use my slides. Just give me credit for that. Okay, tell people my name. I'm the person who created the slides. All right. So how to talk to researchers, research terminology. So I want to do this as a poll. I think we have the ability to do that. So I'm going to create a new poll. Let's see if I've got the option here. Or I can do it on this one, existing poll. Okay. So enter a title. Is oxygen a metal? And that's our question. And the possible answers are yes or no. Okay. So let's give that the old college try. And let's see if we can start up a poll and see what people think. Here we go. Okay, I launched the poll. Is oxygen a metal? How many of you vote yes? And how many of you vote no? And by the way, vote your heart. If you've seen this talk already, don't vote what you know my answer is going to be in the talk. Vote how you feel in your heart.
You're missing the it depends option.
Yeah, well, I want you to vote your heart, and your heart does not depend. What do you really believe in your heart of hearts? Is oxygen a metal? And we're doing pretty good. We got, we're almost at, we got 100, we got over 100 answers. I think that's good enough to get a consensus. So 92% of us, 91% of us, now it's fallen, believe that oxygen is not a metal, and 9% of us believe that oxygen is a metal. And the 91% of us are thinking that 9%, what the heck are they thinking? How on earth could oxygen be a metal? Well, let's find out, shall we? Oh, share results there. Now you can see the results. I will go ahead and stop sharing, and we can continue on with the talk. I'm probably going to do a few more of these polls. They just take a moment. I've got a little bit of spare time in this talk time slot, so it's kind of fun. Okay. So only 9% of you believe that oxygen is a metal. Well, what is oxygen really? Well, it's got atomic number 8. Apparently the chemical term for oxygen is it's a chalcogen, whatever the hell that means. It's, if you don't, at least for life on Earth, for most life on Earth, there are exceptions, of course, but for most species on Earth, You've got to have oxygen to stay alive. You also need it if you want your fire to burn, if you want your car to rust, if you want to have water, you got to have oxygen, and so on and so on and so on. By the way, the chalcogen thing, I don't know anything about that. I got that off Wikipedia. I don't know nothing about chemistry. All right, so how about in astronomy? Is oxygen important in astronomy? Well, in order to answer that question, we have to answer the question, what is the universe made of? 75%, by the way, I'm only going to talk about visible matter. I'm not talking about dark matter because we don't know what it is, but 75% of the baryonic mass of the visible matter in the universe. I don't know what baryonic means. Those of you in the physics or chemistry world probably do. 75% of all baryonic mass in the universe is hydrogen. And most stars are made of hydrogen, right? That's number one. Ingredient number one, if you want to bake a universe, the number one thing you need to bake the universe, like you need flour to bake a cake, you need hydrogen to bake a universe. Helium, the number two thing you need to bake a universe is helium. So it's a noble gas, it's inert, and it's 24% of total elemental mass. Again, whatever the heck that means. And every other element in the periodic table combined for visible matter, not including dark matter, all of the rest of the periodic table combined is about 1% of the visible matter in the universe, about 1%. Okay, how about planets? What's a planet made of? Well, typically the core of a planet is things like iron and nickel. In fact, those are the top two ingredients in the Earth's core, which is most of the Earth's mass, iron and nickel. In fact, it's almost all iron. And then the mantles are things like sand and dirt, and of course water, but underneath the water is sand and dirt. In fact, I found an article one time, I stumbled on an article that said barns are painted red because of dying stars. The stuff from dying stars lands on the Earth, and it happens to have a barn color. And so it's cheap to make barn red paint. And so therefore you end up with paints that are that color because there's so much of that junk lying around because other stars have died. Okay, well, what's a metal? My whole research career, sand and dirt, yes. Well, you know, I think we as human beings, I think if you asked an average person on the street, what is a metal? Ultimately, their definition would come down to it's hard and it's shiny. Now, actually, there's an exception to that, which is mercury is liquid at room temperature, but we don't normally think that much about mercury. Most metals are hard at room temperature, they're solid at room temperature and hard, and they're shiny, right? That's kind of the intuitive definition of a metal. Chemists, of course, have a much more specific definition of a metal. And on this diagram I have here, the yellow bits are metals. The orange bits are semi-metals. Again, not a chemist, don't know what that means. And the green bits are not metals, right? And notice two of the prominent green bits are hydrogen and helium, right at the very top of the periodic table. And then down here, here's oxygen hanging around in the non-metals. So a normal person would say, well, oxygen is not shiny and hard, so that's not a metal. And a chemist would say, and in fact, most scientists would say, scientists and engineers would say, it's not in the metals part of the periodic table, therefore it's not a metal. But to an astronomer, the word metals does not mean the yellow bits of the periodic table. The word metals means other, things that are not hydrogen and helium. Now, how do I know this? Well, when I was a wee lad in grad school, my day-to-day advisor, I had two advisors. I had my computer science advisor, who I didn't see very often. It turned out I was his very first PhD student. I didn't know that until years after I graduated. And I had my day-to-day advisor, who was a cosmologist. In fact, for a good number of years, right up until just this month, I think is his last month, he is the director of the San Diego Supercomputer Center. He's retiring from that, going back to being a physics and astronomy professor at his institution. But he's a cosmologist. And for like 3 years, I sat in these weekly meetings and heard them use the word metals and thought they meant shiny, hard things. And then I found out, after 3 years, I finally figured out that what they meant was not hydrogen nor helium. And it completely changed my understanding of what they were talking about. So to an astronomer, because once you get past hydrogen, specifically to a cosmologist, once you get past hydrogen and helium, it doesn't really matter what it is. And the stuff that planets, which they also deal with, is made of are actually metals in the chemical sense. Then therefore the word metals just means not hydrogen or helium. And this captures something super duper important about what do we need to understand about how to talk to researchers is the way they use words, and sometimes seemingly normal words, may be completely different from how we as research computing professionals use words and how normal human beings use those exact same words. So somebody said, my MS was shaking things, my PhD was breaking things. I'm going to guess that was in seismology or something similar. My MS was in organizing and finding things. Retrieval? I don't know, data something. Okay, anyway. Right. Okay, so that's an example. Here's another example. The word projection. So if you sit down, a mathematician, a psychologist, and a movie producer, sit them down at a table and say, talk about projection. What's going to happen? Somebody tell us. Do you want to do a vote? The votes are fun.
The psychologist will talk about how you put your problems on other people.
Right. So let's actually do a poll about that. So I'm going to create a little poll. There. Does that seem reasonable? Let's do that poll. See if I can get it. There we go. Launch the poll. Okay, go ahead and answer the question.
I guess co-hosts can't chime in there because they just see the your server set thing.
That's okay. There aren't that many co-hosts.
Right.
I like these polls. These are fun. Okay, in the meantime, a couple of chats popped up here. Oh, don't forget a cartographer. Yeah. Well, the cartographers, their definitions are closer to what a mathematician would do or would say. Different definitions. Can't talk to each other. Definitely different definitions. So many vocabulary issues when describing things that are common to IT folk versus research teams. Got to maintain an awareness of that and avoid specific terms that introduce ambiguity. It's very challenging. How do I answer the poll? In the bar at the bottom of your window, there should be a thing for polling. Okay, so we've had 111. I'm going to go ahead and close out the poll. I don't want to spend all day on this. Okay, so 90% of you, sorry, 80% of you said thered be chaos. 20% of you said there'd be understanding. I got to be honest and say I'm with the majority on this one. I think it's chaos. I think they will have no common ground. But more than that, chances are they will not even be aware that they have no common ground because within their discipline, they're so accustomed to using the words in that particular word and vocabulary in general to mean specific things that it doesn't occur to them that other people use the same words to mean completely different things. Okay. All right. So, in mathematics, projection means taking something in a higher dimensional space and presenting it in a lower dimensional space. So, that diagram where you've got two squares and diagonal lines connecting their corners that looks like a cube. It isn't a cube. It's lines on a plane, but it looks like a cube. It's a projection of a 3D solid on a 2D plane, right? That's what projection is, moving from a higher dimensional space to a lower dimensional space. Psychologist, projection means assuming that the other person has the same feelings or experience that you do about some particular thing. And to a movie producer, projection means casting light through a transparent medium or semi-transparent medium to put an image on a screen, right? Which somehow relates to the mathematician's meaning in a very indirect way, has no relationship at all to what the psychologist means. So you're just going to get chaos. Okay, and acronyms make this so much worse. They absolutely do. And thanks for starting that sentence with BTW, by the way. Some of our folks call our regular HPC our secure enclave and AWS the HPC. It all looks the same from where they sit. Yeah, perspective is very, very important. At University of North Dakota, or maybe it's University of Notre Dame, it's North Dakota, Eric. HPC is the high performance center where athletes train to perform better. So you can't use the term HPC because you're just going to create confusion. All right, what's a fluid? So how many of you vote? We'll do a poll about this. Let's do a poll. We'll do a new one here. Okay. So fluids. What is a fluid? A liquid, a gas, both, let's say it as either a liquid or a gas. How's that? Okay, so let's pull that up. And fluids. And go. What's a fluid? I only have one vote for gas. That makes me so sad. Okay, yeah, Lane, you don't get to vote because you're a ringer. You teach fluid mechanics. So notice we're running 19% liquid and 80% liquid or gas, only 1% just a gas. What about, no, I'm not getting into plasmas, because if I say that word, people think I mean old-fashioned TVs. Man, the physical chemist in me is screaming internally about all these questions right now. Good. If this makes you angry, then I'm doing my job. Okay, so David says not a solid. Cats are fluids. Yes, a cat is a fluid. You can pass a cat. Cats are incompressible fluids, for the record, but you can pass a cat through any medium that its head can fit through. That's right. Any porous medium. Okay, or the liquid in blood. That's right. Plasma could be blood plasma. Okay, so let's wrap up the polling here and I'll display it for you. Okay, so we got 19% liquid, 1% gas, 81% liquid or gas. Okay, so how's that possible? Well, you know, when you were growing up, if you got sick, your parent or guardian and your doctor said you should drink plenty of fluids when you're sick, right? Which apparently actually does help. But later on, you went to college, and if you took any physical science or any physically based engineering courses, you learned that the word fluid means not a solid. It means a liquid or a gas. And in fact, in the world of computational fluid dynamics, so if you've got users running OpenFOAM, for example, The single most popular fluid that people study with computational fluid dynamics is the air. It's Earth's atmosphere, right? Airflow over a wing, for example. And the definition that they work from is it's capable of flowing and changing its shape at a steady rate when acted upon by a force. So liquids are fluids, but so are gases. Liquids are specifically incompressible fluids. Gases are compressible. That means you can make them smaller. You can't make a liquid smaller. You can change its shape, but you can't make it smaller. Okay, so an issue of scale. So let's turn our focus. If I study a physical phenomenon that occurs at quantum scale over a period of femtoseconds, so let's see, we got milliseconds, microseconds, nanoseconds. Let's see here, picoseconds, femtoseconds. So that kind of phenomenon, if I study that, how much does gravity matter? And I'll throw that question to Horst, because I know he's a high energy physicist. Horst, in your physics work, how much does gravity matter?
For high energy physicists, not at all, because it's so weak.
Not at all. It is not weak. It holds the universe together. It's like the Force in Star Wars. It binds the galaxy together. But at your scale, it's ridiculously weak. Agreed? Now, how about my cosmology advisor? How important is gravity to cosmologists? Anybody want to guess?
Chat says strong force.
It is super duper strong and important at the scale of the whole universe over its whole lifetime. Super duper important. So what you care about and think about, bother to think about, is driven on to a huge extent by how much it affects the phenomena you study. If you study phenomena where it doesn't matter, you never bother to think about it. If you study phenomena where it's super important, you think about it all the time. Let's talk about the difference between science and engineering. What makes science science and engineering engineering? How are they different? Why do we have a different word for each of those things? Why don't we just have one big word? What does science focus on? Go ahead, somebody dive in.
Henry, I don't know that you actually told people that, hey, it's on the slides. Shout it out.
Oh, yes. I only ask questions whose answers are on the slides. So what is science focused on?
I'm going to say discovery.
It's focused on discovery. What's engineering focused on?
Design.
Design. And I'm going to go a little farther. It's actually focused on constrained design. So art is also focused on design, for example. But engineering is focused on constrained design. And the top two constraints on engineering design are time and money, which really means there's only one top constraint. What is it?
Money.
Money, because? Why
Well,
isn't
you can
time
run out
a
of
different
either, but you're going to run out of money first.
Money buys time.
Because time is money. Exactly. Okay. So engineering is focused on design, and in particular constrained design. Science is focused on discovery. I'll tell you a story. So many years ago, it's probably 15 or more years ago now, I was one of the advisors of a master's student in electrical engineering. And his project was focused on creating some software to do a particular kind of thing. And it was a very useful, valuable project. And it was a very difficult project because he was given some software to build it on top of, and that software was very buggy and was abandoned by its developers halfway through his master's. So when we got to his defense, one of the members of his committee was a scientist. And his first question was, how is what this student did research? And I was the only one in the room who could answer the question because I knew about this discovery versus design thing. And I said, well, in your field, because this was a scientist, a physical scientist, in your field, you focus on discovery. So your mental model for research, your definition of research is discovery. But in engineering, engineering focuses on design, therefore engineering research focuses on design, and creating a prototype is a mechanism by which you can study the design issues. So this student created a prototype in order to understand the design implications, to do research about that design issue. That's how engineering research, even though it focuses on design instead of discovery, is indeed research. So do engineers do research? They definitely do, but their research is about design. Now, could they be doing science research? Absolutely. I know engineers who do discovery. They discover physical phenomena. They're often very application-focused physical phenomena, but they are discovering. But I also know lots of engineers who focus on design. And then what does it mean to do research about software, right? Isn't that just writing software? How is that research? Well, we've learned a lot over the last 50 or 60 years of developing software, and we understand how to do it now in a way that we didn't 50 or 60 years ago. Research is absolutely not limited to science, though. There's a whole lot of non-STEM research, absolutely. What I have found, though, historically, is that most non-STEM, what I would call researchers, don't like to use the word research to refer to what they do. They prefer the word scholarship. And if they're in the arts, they prefer the word creative activity or the phrase creative activity. But I wish there were an umbrella term for those three things, but I've never found one. And I have historically used the word research to refer to all three. Engineers can be collaborating on translational research. We're evaluating how tech engineers created, how tech that engineers created can be used in the community. Absolutely. Yeah, so the research to practice pipeline is very, very important, including in various science fields. So for example, in weather forecasting, there's a lot of science research being done in weather forecasting, but some of it is applied in the sense that the goal is to translate it to actual weather forecasts on a day-to-day basis in real life. Biomedical engineering research, absolutely. There's a ton of that stuff going on. All right, now let's talk about the difference between computer science versus information technology. I was once in a meeting with a bunch of domain scientists, ecologists mostly, and computer scientists. And one of the ecologists referred to what the computer scientists were there for as IT. And there was a dead and very uncomfortable silence in the room. And the ecologists did not realize that the computer scientists were providing that dead silence in order to allow the ecologist to furiously backpedal. So the ecologist did not furiously backpedal, and that did not go over well at all. And so the computer scientists took the time to educate the ecologist about just how wrong that usage of terminology was. It was a very uncomfortable meeting. Wait a minute, computer scientists do research? You gotta be kidding me. I thought their role was to help everybody do the real research. By the way, I've been in that meeting too. It went over just as well as what I had just described. Those things do not go over well. Not only do computer scientists do research, but in many cases, they use a very specific word to refer to the practical outcome, the thing that comes out of the research they do, the practical, useful thing that comes out of the research they do, they refer to as an artifact. Now, what does artifact mean in other disciplines? What does it mean in archaeology? What's an artifact?
Pottery.
A physical object. Yes, and an ancient physical object whose usefulness ended hundreds or thousands of years ago. Something left behind. What do electrical engineers mean by the word artifact?
That's more like an error, right?
Yes, yes, the error term. That's right, something, an error in an observation, right? So artifact does not sound like a good thing, does it? And I don't think CS researchers mean it as a good thing when they're talking about it. They're interested in the research, not the product. I had a chemical engineering colleague years ago, now at another institution, and we were working on a project together, and he was running some code that he and a student had written together, and they were producing some output, and we were using that, and he was writing a paper for a conference, and I referred to the output of that simulation as data, and he stopped me dead, and he said, no, 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 no. I cannot call this data. If I go into that conference and I refer to the output of this simulation as data, I will be laughed out of chemical engineering. I have to refer to this as simulated data. Now, as a computer scientist myself, data to me is anything that can be expressed as ones and zeros. But to a lot of people, the word data has a different meaning from how I mean it. Okay, now, before we get to this next section, I want to tell a story. Very early on, the guy who taught me how to write grant proposals, I mentioned in a previous talk, the guy who taught me how to write grant proposals, one time we were talking and he was describing a thing to me. And after he described it, I said, oh, that's a binary tree. And he said, it's a what now? I said, binary tree. This is like first year computer science. And he said, I've never heard of that. And this was a revelation to me. By the way, this is like 20 plus years ago now. This was a revelation to me that any human being on Earth would not have heard of a binary tree. Now, of course, in retrospect, of course he had never heard of a binary tree. Where would he have heard of that? I heard of it in computer science courses. He didn't take any computer science courses. He had plenty of chemical engineering courses to take. He didn't have time to take computer science courses any more than I had time to take chemical engineering courses. Of course, he'd never heard of a binary tree. But up until he said that, it had literally never occurred to me that any human being would not know what a binary tree was. And it opened my eyes. It changed my life when he said that. All right, I want to kind of go off in a slightly different direction because I want to give you a very useful perspective, okay? The difference between enterprise IT and research computing, are they natural enemies or are they natural allies? And I'm going to give you a preview of coming attractions. The answer is yes. So what characterizes enterprise IT? What characterizes research computing? Enterprise IT, I can distill down to 2 words, 5 nines, right? Everything in enterprise IT has to be secure and established technology and best practices. It's got to be always working perfectly. Because if it's not, you're fired, right? So the goal in enterprise IT, you don't always achieve it, but the goal is 5 nines, 99.999% uptime, which translates to just over 5 minutes of downtime per year. Research computing is the exact upside down of that. Research computing, I'm not making this up, is 1.5 nines, 95% uptime. And I didn't make that up, and I'll explain that in a minute. So what it means is it's got to be fast, it's got to be flexible, you got to be able to turn on a dime. We get requests every week that are completely different from anything we've ever seen before, and we got to be able to react immediately because they don't have time to screw around. They got a deadline coming up, right? It's got to be cutting edge technology. Well, in the world of technology, you have exactly 2 choices. You can have established technology, which means obsolete, or you can have new technology, which means broken. So in the research computing world, we're in the broken technology business. In fact, our vendors are very sweet to us. They pre-break much of the technology for our convenience. Now, of course, they work with us to fix it, but a lot of the times things show up not working right out of the box, and we work with them to figure out how to get it to work properly. In many cases in the research computing world, there is no such thing as best practices. In fact, there's that joke about if we knew what we were doing, it wouldn't be research. And that applies to research computing as well. Now, that that 1.5 nines, 95% uptime, I didn't make that up. That comes directly from the National Science Foundation. 95% uptime, that's 1.5 days of downtime per month, 18 days of downtime. And by day, I mean 24-hour day. So 18.25 times 24 hours of downtime per year. Okay. And this is the NSF standard. So the solicitation that paid for the Frontera supercomputer, the largest academic supercomputer, I think in the world, certainly in the US, Frontera at the Texas Advanced Computing Center at the University of Texas, Austin. That solicitation said for this $60 million NSF funded machine should be unavailable as a result of scheduled and unscheduled maintenance no more than 5% of the time. That means up 95% of the time. Now, by the way, in practice, it's usually better than that. At OU, we do about 99.1% uptime. And our enterprise folks don't quite get 5 nines. They get about 4.5 nines, which means about half an hour of downtime per year. Why? Why is it this way? Well, the answer both for enterprise IT and research computing is the same. Money. It's all about money. Here is an example. So this is now 5 years ago. Delta experienced an outage, a power outage in their primary Atlanta data center. It went on for 5 hours, and they themselves said publicly it cost them $150 million. That's $1 million for every 2 minutes of downtime. $500,000 a minute to be down. Now, at your institution, you're probably, unless you're at the same scale as Delta, you're probably not losing $1 million for every 2 minutes of downtime, but you may be losing a proportional amount of revenue or productivity, even if it's not the same number of dollars. So what are the incentives in the two areas, in enterprise IT, in research computing? What are the incentives? Well, suppose tomorrow is payday, and suppose tonight the payroll system crashes. What's going to happen? Well, the first thing that's going to happen is heads will roll. Well, at least assistant heads, right? So tomorrow, someone's going to be out of a job because there's going to be a whole lot of angry people who were supposed to get paid and didn't get paid. So if you're on the enterprise IT side, from the very first day, you are taught, never let anything go down. It's your job to make sure that everything stays up all the time. And if you can't do that job, you need to find another profession. Research computing is, again, the exact upside down of that. To stay cutting edge, to be competitive, to get your externally funded research proposals funded, you've got to be on the cutting edge, which means you can't afford to be up all the time. If you don't stay on the cutting edge, you're not going to get fired tomorrow, but you will eventually, because you'll be less and less valuable to your constituency, which is the researchers who need cutting edge research computing. So to stay in business, you've got to stay on the cutting edge. You have to support research productivity, not uptime. So how do we resolve this? Well, it turns out in the research computing world, we can afford to be wrong. If something crashes once in a while, not only is that okay, but arguably that's ideal. And I'll get to that in a moment. Now, if you ask a faculty member, do you want to have a lot of downtime? Of course they'll say no, until you offer them the trade-off. And I'll explain that in a moment. So let's say we have a crash. Let's say, or we have a scheduled downtime. And let's say the machine is down for 24 hours. What's the lost research productivity for that 24 hours of downtime? Well, if we think about academic research computing, in academia, who does the research? Is it the faculty doing the research tasks, or is it the students doing the research tasks? And go ahead and shout out your answers. It's students and postdocs. Good. Faculty manage the student and postdoctoral researchers. Now, once in a while, they get to do some research tasks. In fact, Faculty adore their sabbaticals, and they'll come back and they'll rave about how they actually got to do research. But most of the time, faculty are writing proposals, writing papers, or helping their students write papers, begging their administration for resources, whatever it may be. They're rattling the tin cup. That's the biggest job, well, in teaching, of course, but in the research part of their job, that's the biggest thing, rattling the tin cup. It's the students doing the work. Okay, so if you have 24 hours of downtime on your cluster supercomputer or whatever it may be, whatever the resource is, typically we see 10 to 100 grad students on at a time, 10 to 100 users, and they're typically from 5 to 50 different research groups, right? So you're going to lose 10 to 100 grad student days of research productivity for that 24 hours of downtime. Well, what's a grad student cost? I actually had occasion a few years ago to write a proposal with one of the highest paying departments on campus. They were paying about $29K a year for a PhD student, fully loaded with fringe and tuition and indirect costs. That translated to about $60K a year. So 100 grad student days, that's about a loss of about $16,000, right? That's not earth shaking. It's not zero, but it's not earth shaking. But then slice and dice that by 5 to 50 different research teams, and you find that any individual research team is losing between 3 figures and low 4 figures of research productivity for that 24 hours of downtime. Now, do they want downtime? No, of course they don't. But here's the trade-off. So what does it cost to go from 1.5 nines to 5 nines? And by the way, it's not a knob or a slider. It is a switch. It's a toggle. You can either have 5 nines or 1.5 nines. You can't gradually improve your nines. So what does it cost? Well, I used to think it was a factor of 2 to go from 1.5 nines to 5 nines. And then I was meeting with one of the major vendors and I said that, and they laughed at me and they mocked me cruelly and said, it's not factor of 2. They didn't say the word idiot, but boy, could I hear it in their tone. It's a factor of 10. Okay. So let's say it costs 10 times as much to have the same amount of computing capacity, but 5 nines instead of 1.5 nines, which is what they expect it to cost. Does my budget go up by a factor of 10? Do I have 10 times as much hardware money to spend for the same amount of research productivity? How many people? Let's do that as a vote. That'll be fun. Here's a new one. Poll. Create a new poll. Okay. Research computing funding. Does my research computing funding go up by a factor of 10 if I want 5 nines instead of 1.5 nines? Yes or no? I feel like I know how this one's going to go. Here we go. Okay. Go wild. What do you say? I want to get past the 100 mark, so the last few stragglers, go ahead. We're almost there. I just need a few more votes. There we go. Okay. Oh, we got a few. We got several more now. That's nice. All right, I'll end the poll now. And I'll share the results. So can you see the results? 80% of you said, nope, your computing funding will not go up by a factor of 10 to get 5 nines instead of 1.5 nines. So in fact, I'm actually surprised that 20% said yes. I want to work at your institution where you're made of money. At my institution, and I would argue almost every institution, there's a certain amount of money available and they want you to maximize research computing productivity. Okay. So my budget will go up by 0, which means that my researchers will lose 90% of their research productivity. So I actually offered that to a faculty member one time in front of my boss. It was at our annual symposium, big room full of people, including an NSF speaker and so on and so forth. And I said to my boss, I said to the faculty member, Pat, if I offer you 5 nines of uptime, 5 minutes of downtime per year, in exchange for 90% of your research productivity, will you take it? And he said, not if you live to be a million. So when you offer the researchers the trade-off, they understand how right you are. And they'll go with, I'd rather have the downtime in exchange for massively higher research productivity. So as a result, the way we approach this is let the machine go down from time to time, whether for scheduled outages or unscheduled, in exchange for vastly more resources and therefore vastly more research productivity. Because at least at academic institutions, researchers do not get judged on research productivity per day. They get judged on research productivity per year. I undergo 2 annual evaluations, one in my IT staff role, and that's a regular staff evaluation, and one in my faculty role. And I get one of those per year of each flavor. Regular faculty only get one, the faculty evaluation. Once per year, did you bring in enough grant money? Did you publish enough papers? Did you graduate enough students? And are your teaching evaluations reasonable? Right? That's my annual evaluation. I do pretty well because all of those are yes, right? Let me look at some of the comments here. Regular maintenance windows help manage expectations. That's definitely true. So you need to divide research computing into 2 types. Clinical research computing has to be reliable. Yes, clinical stuff. If you're running, for example, an electronic health record system, for example, I consider that absolutely an enterprise capability, not a research computing capability, right? So if by clinical you mean used to actually affect treatments and outcomes, that's an enterprise capability.
Are you on mute?
There should be an unmute button. Clinical trials, I'm less certain about. I myself actually, we're going to be getting to that next year. So what happens if your clinical trial system goes down and you can't enter in the data? So that if there's a paper backup, then can't you survive a day of downtime from time to time? Okay. Not really. All right, I think that's a fair point. And I think if you need enterprise capability, move it to the enterprise side. And I'll get there in a moment. How normal is it to fail in the research computing world? Well, I actually collected this data from calendar 2020 on our supercomputer. So we ran 8.2 million batch jobs. Of those, about 4.5% failed in some way. But only 6,400, about less than 0.1% of all jobs failed because the hardware failed. Lots of jobs failed because they had something wrong in the parameters and the code crashed. This is something we see, for example, very commonly in weather forecasting codes, which are obviously a big thing at OU. We have a big weather school here. But it's quite common that you do the run and partway through the run crashes because, for example, there's a mismatch between how big your time interval is on your time steps versus how fast the wind is blowing. And the code typically does not detect that automatically in order to either adjust it or to fail gracefully. Whereas failing because of an external factor is quite rare. So Failure of a job is normal. Failure of hardware is unusual, to the point where it's really round off error. It absolutely does happen, but it's very, very unusual. Okay. So what are the implications? On the one hand, research computing is much less expensive than enterprise IT on a per unit of research productivity basis, if you want to think of it that way. But it's also a lot less resilient, right? 1.5 nines versus 5 nines. So when we have a researcher come to us for help and they want to know, where should I put my thing? My first question is, can you tolerate several hours of downtime per month on average? If their answer is yes, then I say use the research computing capability because it's cheaper. And if their answer is no, I say use the enterprise IT capability because otherwise you're going to have a lot of trouble, right? And so that question is one of the frontline questions we have to ask the users. How much downtime can you tolerate? So in the discussion that Eleanor is having about clinical research, if clinical research cannot tolerate downtime, or if specific clinical research projects cannot tolerate downtime, they belong on the enterprise side. If they can tolerate downtime, they belong on the research computing side. And that's the way to make that decision. And that's the question that you need to ask the researchers. How much downtime can you tolerate? And here, that's how we steer people. If they say, I can't tolerate several hours of downtime a month, we steer them away from us because we will only fail them based on what their needs are.
Say, Henry, can I ask a interrupt
Please.
question to you?
I love questions. And I love
Okay.
this discussion that's going on in the chat, by the way. Go ahead.
So I'm wondering if this leads towards a debate about cloud versus on-prem, because premise enterprise computing is inherently inefficient in utilization. You have to build enough equipment to handle the surges and at times when it's very busy, and then the rest of the time the compute is often underutilized. So the CIO says, well, let's put it in the cloud, it's more efficient. But I don't think that applies to research computing in the same way.
So I think there's a spectrum of needs, and there are absolutely use cases where cloud computing is superior in all the important ways. And there are use cases where on-premises is superior in all the important ways. And what you have to do is you have to look at the relative advantages and disadvantages. And we actually have a whole session about facilitating cloud computing coming up later this week, where we're going to dig into the details of that. And I do not pretend to have a lot of expertise on that. But my observation at my own institution up to this point is a lot of our folks are interested in cloud in theory, but don't have the money to commit to it in practice. So they're much more likely to gravitate to a resource that is in many ways less convenient for them, but doesn't result in them getting charged. Or if they are getting charged, they get charged in a much more predictable and fixed way. And that's hard to do with a cloud resource. So I'm not going to delve into the details of that, but my point of view is use cloud when it does make sense, use on campus when it does make sense. And those are, in my experience, very different use cases. And we've got some comments in the chat about that. So Amazon's been really helpful for us with specific research funding to use their stuff for much lower cost. There's another one here that I missed now. I'm missing it. Okay. Oh, here we go. Another question is, how soon is your deadline? I have a story about a team that upgraded one piece of software and afterwards the new results were incompatible with the previous 5 to 10 years of research. Yeah, one of the things we do here is we may deploy the newer version, but we don't clobber the old one. The old one's still there, it's just no longer the default. But we leave the old one in production for exactly that reason. Some people get tied to a specific version until they've published that set of papers, and then they can move on to the next version. Take them months to rerun on the older software. They didn't have months, but 2 days in a custom created cloud instance that we spun up and spun down for them. Yeah. Here's the other part of it. And this is why I believe that research, and by the way, everything I've said about research computing right now, when I say it to the enterprise folks, I can see their teeth clench and the chills run up and down their spine and the blood drain out of them, right? What I say about research computing is a combination of terrifying and insane to them. But on the other hand, when I describe research computing the way enterprise folks do stuff, they're like, why would you bother to go to all that rigmarole? How's that going to happen? It's also, it seems crazy, not terrifying. It just seems dumb. But the real answer is enterprise is right for enterprise and research computing is right for research computing. They're different needs that therefore are optimized with different approaches. Okay. And again, I recognize there's some research computing that fits better in an enterprise resource than a research computing resource. These are generalities. Okay. So how can we make them be natural allies when they look like obvious natural enemies? Research computing has very limited best practices, up to and including none in some contexts. But when we're adopting a technology now, that's a technology that the enterprise folks are likely to start adopting in 3 to 6 years. I mean, I'm guessing that those are typical numbers. So if we can make mistakes now, which we can afford to do, and they can't, if we can make the mistakes now and they keep an eye on the dumb mistakes we make, then they can learn best practices from what we did wrong so that they don't have to make the same mistakes we made. They at least can make exciting new mistakes, right? So here's a good example. Back in 2012, I think it was 2012, we moved into our current data center. It was brand spanking new. They had just built it. We were the first IT resource in that data center. Very, very first. Nobody else was in there. It was all empty space, empty racks from one end of the room to the other. And we moved in there. Nobody had tested mechanicals. I mean, they had tested it, but not with actual machines. Nobody had tested the network. Again, they tested it, but not with machines. Certainly nothing had been in production. We moved in there. We told our users it would take 1 to 2 weeks to move in there. It took 1 week and 1 minute. I sent the email at 5:01 p.m. on Friday of that first week. And it was the first week of classes when we did it because the previous week was a short week and people were just coming back from vacation. We figured that was not realistic. We got the whole thing done in a week. It turned out everything was working perfectly. The mechanicals worked great. The network worked great. We got up and running. But the reason we could do that is unlike all the enterprise systems, our systems were not massively, a buddy of mine taught me a great word, not massively intertwinkled together. And so we could pick up our stuff from 5 miles away and move it into the new data center on a truck. And it was no big deal and everything worked great. I mean, something could have gone wrong, but happily it didn't. The enterprise folks could never hope to do that because all of their stuff is intertwinkled. It all interoperates, right? Everything has to pull the Active Directory system and this thing and that thing, right? They're all interacting and interoperating all the time. And unraveling that is fraught with peril. So it takes them sometimes months to be able to pick up a system and move it to somewhere else, or even a virtual machine and move it to somewhere else. It's very, very difficult and very perilous. For us, it's straightforward. So we moved into the data center, proved it was production ready, and they were able to start doing their stuff because we had tested it first. We took the risk because if we'd had an extra week of downtime, sure, everyone would have been annoyed, but no one would have been wrecked. Okay, I know I'm running low on time, but that's good. I'm happy that I'm not going to get through all my material. I'll get as far as I can till we hit noon, and then I'll stop. Okay, so let's talk about the mindset gap. I alluded to this earlier. In the golden years, long, long ago, and by this I mean like 15 years ago, when a new user came to us, they came to us from a Windows laptop background. They might even have done some MS-DOS command line. Well, nowadays, that's not true. Nowadays, they're coming from this, right? They're coming from iOS and Android. They're coming from a phone or a tablet. So what does that do to our job? How does that change things? Well, it's all about the mental distance. And the mental distance from a handheld to a supercomputer, for example, is much greater than the mental distance from a PC to a supercomputer. That's still a pretty big distance from the PC to the supercomputer, but from the handheld to the supercomputer is even more. So think about, for example, if I want to install software on my phone, what do I got to do? 3 taps. I tap once to open the store. I tap once to select the software app I want. And I tap once to give them permission to listen to my phone, right? And from then on, it'll auto update. I don't have to do nothing. It'll just give me a little notification that it updated, right? How about on a supercomputer? What do you got to do? Well, if you're lucky, someone's got Easy Build or SPAC and they can do it for you. But usually what you're going to run into is there's a configure file and a make file, and you don't know anything about that because that's outside your experience because you came from a handheld, right? And it's got dependencies. You got to download other software, and the particular way that everything gets built is bizarre and random and weird, and there's no uniformity, right? There's no such thing as an install wizard. I mean, there is in theory, but in practice, nobody uses it, especially not for research software. It's not even realistic for many of our users that they would ever be able to learn how to do this. Okay, ever. If they wanted to devote their heart and soul to it for a month, sure, but they don't got time for that. They got to get their research done. They don't want to screw around with that stuff. It's really hard. And it's a lot to ask to say, if you don't install your own software, you don't get the software. That's a lot to ask. Some of them can do it, to be sure. Many of them cannot. They come from an iOS or an Android background. They come from a handheld. How about storage? How do you do it on your phone? Well, it's real easy. If you have the slot, you go to the store, whether online or in person, you buy a little tiny micro SD card, you pop open the slot, you push in the little card till it clicks, and boom, you've got storage, right? And it's ready and it's up and running. It costs you tens of dollars, maybe low 3 figures at the outside, but typically 2 figures. And it took minutes. It probably took you longer to open up the bubble package, the plastic packaging with the scissors, than it did to actually install the thing, right? It's trivial, okay? How do you do it in large scale? How do I do that for a large scale research computing resource? Well, I got to do an RFP if it's over $5,000, at least at my institution. So I got to run the RFP. That's going to take at least 2 weeks, but probably a month. I got to write the RFP. That could take easily a couple of months, by the way. I know from painful experience. We got to evaluate the bid responses. Then we have to, if it's over $1 million at my institution, it has to go to the Board of Regents, which injects at least 6 weeks of delay into the process because they require us to submit at least 6 weeks in advance. Depending on when the meetings are, it could inject several months of delay. If it's just we did it several months before the next meeting. Then once we get approval, or if it doesn't need approval, then we have to do configuration. There's back and forth with the vendor we selected. We finally execute a purchase. Then we wait patiently for the equipment to show up. Then we deploy it. And then we got to take care of it. We've got to maintain it, which is labor intensive for its entire lifetime. And finally, we have to decommission it, right? That's totally different from going to a big box store, buying a little card right off the shelf and sticking it in a slot. By the way, if you don't have that little slot in your phone, then the answer of how do you get more storage is you buy a new phone, which ironically is even easier to do, but costs a lot more. Okay. These things are hard. How much are we talking about? Well, okay, so this is a few months out of date, but it's basically correct. A petabyte of raw tape, single copy, is about $6,000. Raw spinning disk is about 10 times that much. Raw SSD is well into 6 figures. And that's like the ultra cheap version of that. That's like the cheapest I could figure out how to do, right? To get a petabyte of SSD, that's amazingly expensive. Okay, switch gears. Why are researchers the way they are? And Bruce is going to go into much more detail about this in his talk in the early afternoon, 1:30 Central Time. So this is just sort of a quick introduction. There are 2 kinds of people in the world. People who split the world into 2 kinds of people and people who don't. there are three kinds of researchers: faculty, staff, and students. And we can break that down further, and I'll go through this a little bit. But let's talk about faculty, because ultimately they're making a lot of the decisions. What do they get rewarded for? What's their incentive? At a research-intensive institution, they're rewarded for three things, particularly in the context of research: bringing grant money, publishing papers, and graduating students. By the way, there's no order implied in that. Well, maybe there is, but those are the three things that they're rewarded for. They are not rewarded for good computing. And in fact, any money they spend on computing is money they are not spending on bringing grant money, publishing papers, and graduating students. So they're implicitly punished for having good computing, in the sense that they would have gotten more reward if only they had focused on those three things. So of course, they don't want to pay a penny more than the absolute minimum, which ideally would be nothing, free. They'd like free. And if they can't get free, they want the cheapest they can get. And I'm not making that up, by the way. Several years ago, we sent one of our team members to a workshop being run by researchers at, I think it was University of Maryland or something, or maybe Johns Hopkins, something out in that neighborhood. And it was a workshop on how to have terrible storage. They didn't call it that, but that was effectively the theme. That is, it was free Lustre on top of free ZFS using consumer grade spinning drives. The idea being to get the cheapest possible storage you could get. And they were quite serious about it, because they could tolerate the loss of some data in exchange for more capacity for the same number of dollars that they had available, right? And by the way, faculty's mental model for what computing and storage cost is what it costs to get a laptop and some USB hard drives at their local big box store, right? At Walmart or Best Buy or Costco or whatever. If you're tenure track, this is very intense. And it's very intense because you've got a clock ticking, and it's ticking very, very loudly. So of course I got to publish a lot of papers. I got to bring a lot of grant money. I got to graduate a lot of students, because if I don't do that, I'm literally fired, right? And I got to get everything going right now, and it can never break, because I can't afford to wait for it to get fixed or set up. In theory, I've got 7 years as a tenure track faculty member trying to get tenure. I've got 7 years, but that's not really true, because that 7th year is the year where I get a buffer year to go find a job somewhere else because I didn't get tenure. So I've really got 6 years, but that's not really true, because the 6th year is the year they're evaluating me, and it takes about a year, right? They send it out to external evaluators. They have internal evaluators. It has to go through several layers of committees and various institutional officers before you're actually granted tenure. So it's really 5 years. Except it takes 6 months to get a journal article published, right? With the back and forth with the editors and so on and so forth. You got to do edits based on the reviewer comments. And they're not going to give as much credence to submitted versus accepted, right, to appear. So really, you got 4.5 years, not 7, 4.5 years. And whatever you can accomplish in that first 4.5 years, that's what you're going to be judged on whether you get to keep your job for the rest of your life, if you want to, right? That's a lot of pressure. There's no time to screw around, right? Okay, well, what if you're tenured? Well, first of all, that mindset has been seared into your brain. And second of all, the same issues obtain, they're just not about whether you get to keep your job. I won't get if I don't do these things, I won't get my raise, I won't get the named chair, I won't get elected to the national academies. So it's the same thing, right? I got to have it working now. It's got to work perfectly all the time, right? I realize that runs counter to research computing is allowed to go down from time to time. It's a balancing act. What if I'm research faculty, not traditional tenure track faculty? Well, research faculty have to bring in their own money, right? So if I don't bring the grant money, I'm fired. Well, laid off, right? I got to publish in order to bring in the grant money, because if my results from prior support show no publications, then I don't get the next grant. And I need a track record of graduating students, research assistants typically, because I want to get a tenure track job somewhere, because I don't want to live on soft money forever. That's really hard. I've known people who've done it. It's very, very stressful. If I'm a postdoc, it's largely the same thing, right? I got to publish, or I'm not going to stay a postdoc very long. I got to learn how to get grant money, even get a small grant of my own, because I want to use that. I want to leverage that experience to be able to get a permanent position, a tenure track position somewhere, ideally. If I'm a student, my number one job is to graduate. Anything that delays my graduation costs me money. I might have an assistantship, but it doesn't matter. So when I went to grad school, I calculated the opportunity cost associated with going to grad school and completing my PhD between $250,000 and $500,000 of foregone salary and benefits. Not including the interest that might have piled up, because I didn't have a lot of expenses back then, right? I could have lived like a student even though I was a professional. Between $250,000 and $500,000 is what it cost me to get a PhD. And I never paid a penny in tuition or fees, right? I just paid for my living expenses. And it still cost me 6 figures. Is it easy to get grant money? It sure isn't. So for the most recently completed fiscal year, which ended in October of 2020, it was 28.5% of NSF proposals were actually funded. It varies a lot by discipline, but that's a pretty good way of thinking of it. And the full range looks to be between 23 and 42%, depending on the discipline, right? So more than half the time, sometimes 3/4 of the time, you will not get the grant proposal funded. So the only way to survive is to submit lots and lots of proposals. And in fact, this varies hugely by state, right? Where you are has a big influence. Not in a direct sense. People don't go, oh, that person's from Oklahoma, we're not going to fund that. No, they don't do that at all. It's just that the kinds of institutions, the kinds of research that they have going on, and so on and so forth, affect the probability of success. What programs can you apply to, and so on and so forth. So we see anywhere from 20% in Mississippi up to 40% in Alaska and DC, right? It varies enormously. My state, you can see here, where'd Oklahoma go? On the low end, 24% of Oklahoma proposals get funded, less than 1/4. So one of the things at my institution we don't do is we don't ask faculty to write proposals to use the supercomputer that we've already paid for. And the reason is they've only got a certain amount of time per year to write proposals, right? They got a fixed number of proposal writing hours per year. If they spend that time writing proposals to use a machine that the institution has already paid for, that's time they're not spending getting external funding into the institution. We want them to bring in outside funding, not get permission to use the machine. So we don't have them write proposals for supercomputer time for that reason. Okay, and we're out of time. We can take a few questions. I didn't have time to read through all of the chats, but shout out questions. We'll take a few and then we'll wrap up and take our lunch break, and then we'll return at about an hour and a half from now. So that's 2:30 Eastern, 1:30 Central, 12:30 Mountain, and 11:30 Pacific. I know we have some folks out in Hawaii. I think it's 2 hours earlier than Pacific in Hawaii at this time of year. I won't swear to that. Okay. Will you cover the rest later? No, we are solidly booked the entire week. There is no time to cover anything else. But I love questions, so ask me questions. And hey, I got through almost 2/3 of my slides. That's not too bad.
For anybody who could hang out at lunch, would you be willing to continue the deck, or do you need a break?
I can go a little farther, but I don't want to press my luck on this. Do you want me to go a little farther into the lunch break?
I would love it.
Okay. Do we want to pause and give people 5 minutes to like microwave their food or run to the restroom or whatever?
This would also be great. Yes.
Okay. I'm going to hit pause on the recording, and then we will pick up 5 minutes from now. So take your quick break, come back. I'm not going to go all the way through the rest of the deck, but I'll go part way through the rest of the deck. How's that? And we'll do 5 or 10 more minutes. Okay, we're back. All right. I'm not going to do the full rest of the slides because there's a lot of material. I'm going to try and keep this down to a reasonable amount. I want to give people a decent break, but let's just pick up and we'll do a little bit more content and then move on. Oh, and I'm missing the chat window. Hang on just a second. Let me pull that up. Okay, there we go. Okay. So what to say to a researcher? When you're talking about cost, what a researcher wants to hear is, here's another way you could do it that's going to be cheaper than how you're currently doing it or how you plan to do it. Or for that amount of money, here's a different thing you could do that's going to be so much better than the thing that you're thinking of doing. Both of those are good, as opposed to, you must do it this other way, which costs more. They're going to hate that one. So don't do that one. They really do want to have control over their part of it because they need to be able to pursue their things on their deadline. So you get to decide how you use your part of it. You can share it with whoever you want to share it with. Those are things that are very attractive to researchers. Doing the administration of it, telling them your students are not going to have to spend their time taking care of this thing. Instead, they can focus on doing their research. That'll improve your team's research productivity, and your research productivity, again, is something that they really enjoy hearing. All right, now, how do you find researchers at your institution? It turns out there's a very straightforward but labor-intensive way to do this. Most academic institutions, if you go to the homepage, the website, there's usually a link called academics. And usually you can drill down into that and find the individual departments' web pages or websites. And then usually you can find a faculty or people link, and you can find the faculty in that department. And you can read, at research intensive institutions, there'll typically be a description of their research area. And you can read that, and you can start looking for keywords. Now, what keywords you're going to see will depend on the discipline they're in. But the things that we see a lot of: computational, numerical. This is especially in engineering, you see numerical a lot. Parallel shows up mostly in computer science. Informatics, you see that a lot in biosciences. Chemistry, look for, used to be you had to look for physical chemists. Now people will actually admit to being a computational chemist. My experience was, for the longest time, probably for the first 15 of the 20 odd years I've been doing this, they would not admit to being computational chemists on their webpage. They would call themselves typically physical chemists. Now I actually do occasionally see someone list themselves as a computational chemist. For a long time, it looked to me as an outsider like there was some kind of stigma associated with calling yourself a computational chemist. I think that's gone away, but that certainly seemed to be the case for the longest time. Biochemists also, some of them are typically big data users, and sometimes big compute users. There are other keywords, but those are probably the biggest ones. And over time, when you've looked at a lot of these web pages, you start to get a feel for what are the words that you would find. In chemistry, they don't say compute, they say calculation. If they say they do a lot of chemistry calculations, they're referring to computational stuff as a general rule. Okay, now you found them, what do? Send them an email. Tell them what you do. If you're writing a proposal, which is the best time to get in touch with them, tell them what program you're submitting to, what the due date is, and how much money is on the table, because that's really going to get them interested. If they can get even a little bit of credit for that expenditure, if you get that money, they will love you, especially if their labor input is very low compared to a typical proposal that they write. Because a typical proposal that they write, they're going to devote months of labor to, not all day, every day, of course, but let's say hundreds of hours of labor to writing a new proposal of their own. If they can reduce their labor costs down to a few hours and still get some credit for the expenditure, oh, you are a hero. Ask them what they need, right? In the context of this thing that I'm interested in, or just in general. What compute needs do you have? What storage needs do you have? What network needs, whatever it may be, right? Ask them what their needs are. This, of course, was paused a bit during COVID, but now at many institutions, things are opening up, especially starting in the fall. And we're going to, excuse me, we're going to start seeing faculty meet and greets again. So if there's some kind of event that your institution holds for new faculty, is there faculty development workshops, things like that, places where you can go and meet people. That's a great way to make contacts. And if you go somewhere and you get a free lunch, because they often hold these at lunchtime, and in exchange for that, you get 3 new contacts, that's already paid for the hour, right? The lunch probably paid for the hour, but plus you start to get to know the faculty better, and just knowing faculty in general, the faculty at your institution will give you insights that are very valuable. And Bruce is going to talk about some of the kinds of insights that you can get about faculty. Go visit with them. Again, this paused during COVID, but now this is going to be easier to do getting into the fall at many institutions. Not every institution, but many institutions. And over time, it will become more normal again. Take them to lunch. There is nothing better than taking a faculty member to lunch. They will tell you stuff. And by the way, if you offer to buy them lunch, there are people who will turn down a free lunch, but there aren't many people. Most people will take your offer, absolutely. And if you can get your institution, your boss or whoever to pay for the lunch, that's even better, right? And ask them just open-ended questions like, what's your research about? What are the computing or the data parts of it that you're dealing with? And here's one of my favorite. Hypothetically, because of course we'd never be able to offer this in practice, but hypothetically, if we could offer you an infinitely large, infinitely fast computer, what research would you do then that you can't do now? Because the thing is that in my experience, researchers think very practically, here is what I can get now. So that's the scale and scope of my ambition. And I'm not going to spend a lot of time fantasizing about what I could do if I had more, because I ain't going to get more. And you want them to do that. You don't want them to start at what you can do now and inch forward. You want them to start at where they can get to and then pull backward so that they have a plan for what they're going to do and how they're going to get there. You want them to have big ambition. Among other things, that wicked, selfish, mercenary reason, that's your job security. Okay. Now, Dirk has a whole session tomorrow where he's going to do about 15 minutes of material on doing intake interviews. And then he's going to run the intake interview practicum. And we're going to practice doing intake interviews with real researchers and with some simulated researchers. When you get into a room with researchers, you ask them specific open-ended questions. And I will argue that it doesn't matter what the questions are. They should be specific and open-ended. They should not be yes/no questions. And the reason for that, and my experience has been, if you approach them and you ask them the questions you really want to know the answer to, they don't know how to articulate the answers. But if you ask them questions that in many cases you don't really care what the answers are, or they're not that big a deal, that will trigger them to talk both about the things that matter to them and talk about the answers to your questions in a way that telegraphs the things that are important to them. So one time we sat down with a research team and we got through, in an hour and a half, we got through 9 questions. And those 9 questions got us 9 pages of notes about what they cared about. And at the end of that, we understood them really well, even though we'd never said to them, what in the computing and data intensive parts of your research, what's important? What do you care about? If we had asked them that question, they wouldn't have known how to answer. But by asking the question indirectly, What language did you write your software in? Or did someone else write it? Is it in parallel? Who wrote it? What operating systems can it run on? What's the science problem? What's the numerical method or the algorithm you're using? How much RAM does it use? How much disk does it use? How many time steps does it take to run an experiment? How many experiments do you want to run per year? Those questions don't matter. I mean, they do, but they matter like this. The big questions are what's important? What do you value? What do you need? What problems do you need solved? And those questions will emerge from the discussion. Okay, I got one to add to the list. Tell me the story of your research and where your pain points are. Absolutely. Yes. Right? But get them talking. Get them talking about specific things, whether they're the things you care about or not, because the things you care about will emerge from that part of the conversation. Okay. I think let's leave it from here. There's more material here, more about writing grant proposals. I'm going to leave it out for now. We've done it in previous years, and we can do it in a session outside of this week's workshop if you guys want. Just, if y'all send me hate mail saying we need to do this, we can set up a session during the summer and do something about it. We've done that in the past. It's been very popular. Happy to do that. But let me give you a little, you got a little over an hour left on your lunch break. So in about an hour and 8 minutes from now, we'll come back and Bruce is going to talk about the faculty perspective, and he is faculty in physics here at OU. It's going to be very enlightening for those of you who have not been exposed to these kinds of things before. Let's open up our brains, open up the world to ourselves. Let's learn about this stuff so that we can be more effective in helping them be more effective and efficient researchers. So we're going to take a break. We'll see you in a little over an hour at half past the hour, just over an hour from now. We'll see you then, and we'll move on to our next session. And I'm going to leave this session live. I'll turn off the recording. I'll turn off my screen share. I'll leave the session live, so people who want to chat during the lunch break are welcome to do so.